All right, so we have this chart that we need to fill out. It's going to tell us exactly all that we need to know about VSEPR. This is otherwise known as molecular shapes. So if we have two bonds around a central atom, so if I draw me a central atom right here, and I draw two bonds coming out of it, those bonds are going to space out on that atom, so they are as far apart as possible. And so the way it's going to look is like this right here. You can reference the PhET that you did yesterday. The name for that is linear. If you have three bonds, all right, so if you tried on the PhET yesterday, if you take and you add another bond to this, it comes in and it actually forces these other atoms apart, and so it's going to force them to sit in a shape that looks like this. We describe that just like it looks like a triangle, and so we call that trigonal. And they are all in the same plane, so we call that trigonal planar. All right? If I remove one, for example, that top one, and replace it with a pair of electrons, we now have an unshared pair on that central atom, and it's going to look like this. There's our central atom, and it's got a couple of electrons up top, and then this bond and this bond didn't change where they were. They stay right where they are, and we call that shape bent. If I'm memorizing shapes, by the way, what you need to do is you need to memorize the first shape that has 0 unshared pairs. Then all you have to do is take one of the bonds away and you can get the next shape down. So make sure you memorize those two shapes right there. All right, for the fourth shape, this one's tough. What we have is in a in a 4-atom molecule, 3 of those, right? There should be 4 atoms bonded to a central atom. So that's actually 5 total atoms. 3 of those have to be in the same plane. So that would be these 3 molecules. But if we do another one, and if you did this on the 3D PhET, you saw this, one of them comes in and attaches like that. That is what we call a wedge. There we go. Draw it a little better there. That looks like a wedge right there. And it shows that this one is coming out of the page at us. And then to show one going into the page, we draw a dashed wedge. And that one's attached to that atom right there. And that one's going in to the page. This one's coming out of the page, and that one's going into the page. Out and in. This shape is defined by the fact that it has 4 faces. There's a face here, a face in the back, a face up front, and a face on the bottom. That's 4 faces, so we call it tetrahedral. Feel free to pause me anytime. I'm going to keep moving. If I take one bond off, I'm going to take the top bond off. The rest of it looks exactly the same. Oh, don't forget to star that one. Let's star that one. The rest of it looks exactly the same. Oh, goodness. Oh, that is a horrible dashed wedge. And by the way, I'm terrible at drawing dashed wedges. You don't have to be great about it either. I know what that means if I see a dashed line like that. I know what that means, and most chemists do too. This shape now looks like one of those things that you find in Giza, built by the ancient Egyptians. But it's instead of having a square base, it has a triangle base, so we call this one Trigonal Pyramidal, like a triangular pyramid. If I take one more bond off, it's now going to look like this. And we got the 4 dots on the central atom, and that is, of course, called bent. 5 is really hard to see, but if you got your central atom, and there are 3 atoms that we can actually put in the plane on this, one comes out the back, one goes into the paper out the back, just like that. This is defined as the fact that it's 2 triangular pyramids put together, so we call it trigonal or triangular. By the way, some folks you'll see call this one especially triangular bipyramidal. And some folks call that bispyramidal. It's all the same thing to me. Spelling doesn't count in shape names, just as long as I can tell what you mean. If we take one off, believe it or not, we're going to take off this front-facing one. So we're going to have to draw another dashed wedge. Doggone it, why did I pick that one, right? There we go. That's actually probably the best dashed wedge I've drawn in my entire life right there. We're going to put those electrons on there. Believe it or not, this shape, when you make it in 3 dimensions, if you imagine these two are the legs and these two are the bench, this looks like a seesaw. And that is literally the shape it's called. It's called the seesaw shape. Now we remove that backwards facing bond right there, and we get a molecule that looks like this. Except now it's got 4 dots around it. And if you turn on its side, you can really see that shape right there. That is, I pity the fool who doesn't recognize a T-shaped molecule. I pity the fool. And now we take off 2 more. It's going to be these 2 over here on this side. And I'm going to kind of turn it flat because it makes it easier for me to draw. But this guy is a perfectly straight line. And we're back to linear. All right, last but not least, 6. 6 go perfectly 90 degrees from one another. All 6 atoms attached to that central atom are all going to be 90 degrees from one another, including 3 dimensions. We have to have them 3-dimensional. Octa, there we go. Hedral, look at how wonderful that handwriting is. This is defined by the fact that it has 8 faces. Octa meaning 8, hedral meaning face. And then if we take 1 electron away, I'm going to take the 1 off the bottom, so that I can squeeze this down here on the bottom. We're going to make it a pair of dots. Make that bond out, make that bond out. Look how straight that bond I drew is. It's a perfectly drawn bond. Oh, and that's a perfectly drawn dashed wedge. Perfect. They're Po-body's nerfect, right? Po-body's nerfect. Anyways, this is now looks like one of those regular pyramids, so we call this square pyramidal. And last but not least, we're going to remove 2 more dots. Remove a bond, replace it with 2 dots. There you go. And we are going to take the ones that are forwards and backwards because I'm tired of drawing these stupid wedges and dashed wedges. And this looks like a square, but it's all in the same plane, so that one is square, planar. Again, don't memorize all of them. Just memorize the basic shapes, and you can derive the other ones. So what am I going to do with this? Well, if I have a well-drawn molecule, like, for example, PCl5. So here's my example of PCl5. If I look at it, what I'm going to do is I'm going to count. I'm going to look at my central atom, which for this is phosphorus. It's the one in the center, right? I'm going to look for the bonds on there. And I'm going to look for unshared pairs. That is dots that it has around it, paired up, right? How many bonds does it have around it? Well, it has 5 bonds, and it has 0 unshared pairs. So we're going to look at what shape that is. I happen to have it right here. There's 5 bonds, 0 unshared pairs. The name of that shape is Trigonal Bipyramidal. Good enough. All right, so there's Trigonal Bipyramidal. So if I want to draw this thing, what I'm going to do is I'm going to put phosphorus in the middle, and I'm going to put the chlorines around it in this configuration right here. So that's what I'm going to do on the back of this sheet right here. I'm going to put phosphorus in the middle, and it's going to be bonded to these chlorines, just like this. And then we have 1 chlorine coming at us, and 1 chlorine going away from us. Well, close enough. Technically, this chlorine should go up like this. Yeah, there we go. I like that look better. There we go. Except for the fact that I marked something out of it. But you know what? Po-body's nerfect. That's what we say. Po-body's nerfect. So that's what I want you to be able to do. Notice we don't worry about any of these extra electrons, right? There were a whole lot of extra electrons all around these chlorines, but we don't have to worry about those. Only worry about the electrons around your central atom. And that's how you work a VSEPR problem.